In this video, we're going to talk about the Arrhenius equation. So the Arrhenius equation deals with reaction rates and temperature. Typically, as we increase the temperature of a reaction, what will happen is the rate of the reaction will increase. So we talked about in previous videos how to write a rate law for a reaction, and the rate law includes a rate constant. That rate constant K is dependent on temperature. So when we give a rate constant for a reaction, we need to specify what temperature that data was measured at. K is not going to be the same value at different temperatures. So for example, if we look at something like the reaction of solid magnesium metal with water, that breaks down to magnesium ions and hydroxide ions and produces hydrogen gas. If we do that reaction in cold water, nothing happens. We have to do it at a high enough temperature for this reaction to happen. So this reaction, whether or not it even goes at all, depends on the temperature. So when we look at a reaction, our reactants have some amount of energy to start with, and our products have some amount of energy. So this reaction is drawn for an exothermic reaction. We released energy, and the products are at a lower energy than the reactants. But to get from the reactants to the products, we have to go through a transition state, where the bonds are broken between the reactants and bonds start to form for the products. So we have to go over this transition state for the reaction to progress. As we increase the kinetic energy of our reactants, and one way we can do that is by increasing the temperature. In fact, that's the easiest way to do that. Then we increase the average molecular speed, therefore we get more collisions. So at a higher temperature, often the activation energy is much lower. So we get more of our reactant going to product. So we can write a reaction, we can write an equation that expresses the temperature dependence, and that equation is known as the Arrhenius equation. The Arrhenius equation says that our rate constant is equal to some collision frequency factor, which is a constant for a given reaction, but it's very specific to that reaction and to the temperature, times a lowercase e, which is like the natural log e. There's a button on your calculator for that, to the negative of the activation energy divided by the gas constant times the temperature. Now the gas constant is not the same one that we use for the gas laws. The gas constant in this case is 8.314 joules per mole times Kelvin. You don't have to memorize this, you will be given this value. So as usual, we don't like things that are in a format that doesn't allow us to graph them. So we don't leave it in that format, we rewrite it. So we can rearrange this equation, and it takes some calculus and algebra to get there, which we're not going to worry about because all we actually care about is the equation. So the natural log of K, which is the rate constant, is our Y. That's equal to negative EA over R times 1 over T plus the natural log of A. So we plot the natural log of K as our Y value, 1 over T is our X value, and that means the slope is equal to negative EA over R, and our y-intercept, B, is the natural log of A. So if we were to plot this, you would get a slope that's equal to the negative of the activation energy over R. And R is a constant, so if we take the negative of the activation energy and we multiply this by the negative of R, then we get just the activation energy by itself. So if you have this graph of the natural log of your constants and 1 over your temperatures, you can use that data to calculate the activation energy. So this is exactly the type of plot I was talking about. We would have 1 over T, and our temperature has to be in Kelvin, since our value for R includes Kelvin in the units. So we would plot 1 over the temperature, and then we plot the natural log of K, and the slope of this graph would give us the negative of the activation energy over R. So we are going to wrap up here, and we will get some more practice with the Arrhenius equation in class.